It's funny, we're kind of wired to think in straight lines, but reality, it hardly ever works that way. In this explainer, we're going to dig into why that's a huge problem and explore how we can model the complex curves that really drive everything, from our salaries to the stock market.
So let's just start with that one big question. Is reality a straight line? I mean, think about your career, or the economy, or pretty much anything important. It's almost never a simple, predictable path upwards, is it?
And yeah, a lot of the time the answer is a definite no. Just look at this chart. It shows income versus age. You can clearly see the data points form this nice natural curve. But what happens when we try to force a simple straight line through it? Well, our basic linear model just plows right through the middle, completely missing the real story of how our income tends to rise, then plateau, and maybe even dip a little later in life.
And this gets us right to the heart of the matter, the limits of linearity. Understanding why these simple straight-line models often fall short is the absolute first step. And it's crucial, especially in fields like finance or healthcare, where making an accurate prediction can make all the difference.
This quote just nails the fundamental trade-off we're always dealing with in data modeling. Linear models? Yeah, they're super easy to understand. If this goes up by 1, that goes up by 2. Simple. But that simplicity is also their biggest weakness. They're rigid. To get a prediction that actually matches the real world, we need to embrace models that are more flexible, even if it means they're a little trickier to explain at first. Okay, so if straight lines are out, how do we start bending that line to actually fit our data? Let's open up our first toolkit and look at a couple of really intuitive ways to add that flexibility we need.
The most straightforward approach, the first thing you'd probably think of, is to just add curves directly to the model. This technique is called polynomial regression. So instead of just using age as a predictor, we can throw in terms like age squared or age cubed. What this does is it gives our model the freedom to create a much more flexible curve that does a way better job of tracking that natural rise and fall we see in the data. But of course, polynomials aren't the only tool in the box. On the left, you've got that smooth polynomial curve. It looks great, but it has a tendency to get a little wild and unpredictable at the very edges of the data. Now on the right is a totally different approach, step functions. These work by just chopping the data into different groups, or bins, like different age brackets. This is actually perfect for capturing sudden jumps or thresholds. The downside? Well, you get this very unnatural staircase effect that doesn't really feel how things work in the real world.
So, if polynomials can be too wild and step functions are too clunky, what's the answer? Well, this brings us to a much more elegant and powerful solution, the genius of splines. This is a really sophisticated technique that gives us all the flexibility we want, but with a whole lot more control.
So what exactly is a spline? Honestly, the best way to think about it is like one of those flexible rulers that an architect might use. It's a really clever method that fits different, simple little curves to different parts of the data, and then, and this is the magic part, it connects them all perfectly smoothly at specific points that we call knots. It might sound complicated, but when you break it down, the process is pretty intuitive. First, you just pick a few strategic points in your data. Those are your knots. Second, you fit a simple, well-behaved curve in the space between each pair of knots. And finally, you use a bit of clever math to make sure that where those pieces connect, the transition is perfectly seamless with no weird bumps or breaks. And what you get from this is really the main advantage. The result is a model that has tons of local flexibility. It can bend and curve wherever the data needs it to, but it stays stable and controlled overall. It's really the best of both worlds. You avoid those crazy, wild swings you can sometimes get with a single complex polynomial, a problem we call overfitting, where the model starts fitting the noise instead of the actual signal.
Okay, so this has all been great, but we've only been looking at one variable at a time, right? Like age. But real life is obviously way more complicated than that. So that brings us to the full picture. Generalized Additive Models, or GAMs for short. These are what let us handle multiple factors all at once.
A GAM is basically a supercharged linear model. Think of it as taking our old, trusty linear model and giving it a massive upgrade. It lets us use these awesome flexible functions, like the splines we just talked about, for each of our different predictor variables. Then it just adds all of their individual effects together to make one incredibly powerful prediction. Let's look at a real example to make this concrete. Say we want to predict someone's wage. We can build a model that uses a smooth spline function for age. That's the S of age part, you see? And then just add the simple straight line effects of the year and their education level. We're combining the curvy, complex relationship of age with the simpler effects of other variables, all inside one single elegant model.
Okay. Whew, we have covered a lot of ground here. So to pull this all together, let's just make a simple cheat sheet to help us remember which approach might be the right one for the job.
Let's just walk through this real quick. Your basic linear model is that straight line. Super easy to interpret, but as we saw, it's usually too rigid. A polynomial gives you a single curved line. It's a simple way to add some flex, but you have to be careful because it can overfit really badly. Splines give you those smoothly connected curves. They're incredibly flexible and controlled, though figuring out where to put the knots can sometimes be tricky. And finally, GAMs. They let you add all these flexible pieces together, which is amazing for modeling complex systems. Their one main weakness? They assume each factor works independently. Like the effect of your education is the same whether you're 25 or 55.
So the big takeaway here is simple. Reality isn't a straight line. By using these more flexible tools, you can move way beyond simplistic assumptions and start modeling the world as it actually is. So now that you can see beyond the straight line, what hidden patterns are you going to go out and uncover?